Welcome to this last module on superconductivity. This is the solid state physics course will end after this, and this will be done as briefly as possible and will not have the the flexibility and freedom of going very deep into this. But if you are interested in superconductivity, I have another MOOCs course which deals only with superconductivity, and the BCS theory in particular has been done with some rigor. So, we are again present you with this periodic table, and where there are these materials which are shown here, these materials that are present really here that you see there. So, not the ones that are here, but on this top row, and they are either magnets or they are superconductors. Okay. So, the left side is more like superconductors and the right ones are like more like magnets, and of course, there are some superconductivity on the right side as well. So, this looks like that they exist on the same row, which means that there are a lot of properties that are common, and indeed there are properties that are common. There are these niobium, which are one of the first known superconductors, niobium with a Tc of less than 10 Kelvin, platinum with very low Tc, a fraction of a Kelvin. These mercury, which was 4.2 Kelvin, and then there were more complicated or rather compound materials, or there are combination of different elements which gave rise to superconductivity. The Nb3Sn and Nb3Ge were known for quite some time, and these Tcs that you see 18 and 23, these were the highest known Tcs till about the mid 1980s. Okay. And there are more, there are other superconductors, and this has been taken from this superconductors.org. And this Kamerlingh-Onnes, who discovered superconductivity, this shortly after this liquid helium was discovered, and he passed current. So, this his name is Kamerlingh-Onnes, K. Onnes, passed a current through a very pure mercury wire and measured the resistance as he steadily lowered the temperature. So, the temperature of the substance is steadily lowered, and he was measuring the resistivity of very pure mercury. So, this mercury has been all kinds of defects, etc., impurities have been removed as far as possible, and it is in a very pure form, and he was measuring this resistivity. And what he found is that there is no resistance below a certain temperature, 4.2 Kelvin, and implying that there is a very good conduction, or there is this name superconductivity arose there itself or thereafter, and one gets these extremely good conduction where the he saw these thing to go to 0, nearly to 0, 10 to the power minus 5. And the question is that is the resistance really become equal to 0, and it is really, because a lower limit of the decay time of current that flows in the system is equal to 10 to the power minus 10 to the power 5 years. So, current that starts in a superconductor will go on for 10 to the power 5 years. So, it is that kind of precision we are talking about in terms of defining the resistivity to be equal to 0. So, what can kill superconductivity, or what are the agencies that can kill superconductivity? Of course, you need to provide enough energy for all the pairs that causes superconductivity. We will come to that. All pairs within some coherence length. So, the pair should be broken and the superconducting state should be lost. It can be done using thermal energy, which is there is a critical temperature Tc, or you can actually give a current in the system, pass a current in the system. If the current exceeds some critical current density Jc, then also superconductivity will be destroyed, or the superconductivity can also be destroyed by using a critical magnetic field Hc. Okay, so what is superconductivity? What happens in superconductor? How does a superconductor form? What is a microscopic picture, and so on and so forth. Okay. So we start from this right picture as you see there. So there is a inner circle which is slightly shaded or striped. That's the filled Fermi sphere. So the filled Fermi sphere, we have these two electrons. Now we are showing it in K space. So they correspond to the two momenta having this momentum k and minus k, that is why they are shown in opposite side. They just go out of this and remain in the vicinity of these this Fermi sphere, and if that happens, then if they sort of stay within a distance h cross omega d, where omega d is a Debye frequency, then such a thing, the pairing of these electrons can be formed. And we just talking about 2 electrons, and we can talk about 2 more electrons independent of these 2 electrons, and 2 more, and so on. So if you have n such electrons there and n by 2 pairs are formed, then this it will result in a superconducting state. Okay. So we crucially need a filled Fermi surface, and we should have a lot of available space for scattering or states for scattering. Okay, so this is a metal T greater than Tc, and we have so these all these in metals, the electrons are filled all the way up to the Fermi energy, and in a superconductor, as you lower the temperature, what happens is that sort of gap is created, an energy gap is created at the Fermi level. Okay. And these density of states get slightly modified there, and these electrons which were earlier there, they sort of occupy this state. Okay. Now, if you switch on certain kind of interaction or rather certain kind of attractive interaction, normally attractive interactions do not occur between electrons. Electrons are known to give rise to repulsive interaction because they have the same charge. So, the Coulomb interaction between them is positive and will not give rise to superconductivity, but there are another agency or a sort of a third party which plays an important role in pairing, and this third party is nothing but the lattice or the phonons. Okay. So, let us see what is written here. So, the density of states at the Fermi level, we can denote it by DEF, it plays a crucial role. These are the most unstable electrons in a solid, the ones that are here are the most unstable electrons, the one that are here showing so laser pointer, yeah. So, these are the most unstable electrons, and these electrons would want to sort of they easily rearrange themselves to lower their energies, and so the electrons near the Fermi level are able to lower their energy when the superconducting gap opens up. That is this area that you see here, that is this area here. So, each electron gains this energy delta, and a pair gains this energy 2 delta, and the number of electrons that are involved is proportional to this hatched area, which is something like half Eg into density of states at the Fermi level. Okay. So, what is important is that you should have a filled Fermi C, and then certain agencies can create these attractive or induce this attractive interaction which will cause superconductivity. Let us see some development of superconductors. In 1935, the London brothers, they proposed 2 equations which are known as London equations. They are very important in the study of electrodynamics of superconductors. In 1950, the Ginzburg and Landau, they are 2 Russian physicists, they proposed a phenomenological macroscopic theory. These are called the GL theory. In 1957, the BCS theory, which is a microscopic theory and a variational theory that was proposed. And 1986, there are these Bednorz and Muller, they discovered superconductivity at very high temperatures, and these are called as Cuprate superconductors. And since then, there are large number of superconductors that are discovered, organic superconductors, magnesium boride, pnictide, arsenide, several topological superconductors, they are discovered. And Superconductivity has always been at the at the forefront of research, because it has shown up many surprises. Some of them were understood using some microscopic theory, some of them could not be explained using microscopic theory, and we had to be contented with whatever applications they had to offer. And each time there is a discovery of a new superconductor, there is a surge in the research interest from all across the world, where people either want to recreate or reproduce that superconductor, fabricate that superconductor, or want to find out whether the theory aligns with the well known BCS theory, or there is something more that is required. And that is why it is always at the helm of affairs in terms of research. One of the main effects of superconductors, this was discovered by Meissner and Ochsenfeld in 1933, and it's called as Meissner effect, or it's also called as the Meissner-Ochsenfeld effect at times. And what it says is that if at T greater than Tc, you have these flux to be penetrating through the sample, if you lower the temperature below Tc and it becomes superconducting, then the flux will be pushed out. So, you will have a large flux density in the near vicinity of these superconductors, and that is why these superconductors are known as perfect diamagnets. And what is meant by perfect diamagnets is that their susceptibility is equal to is nearly equal to 1. Okay. Even for the best known, the ones that are known in solid state physics, diamagnetic susceptibility is weakly diamagnet. These all of them are accepting the superconductors. So, they have susceptibility of the order of 10 to the power minus 4, 10 to the power minus 3, and so on. So, if you apply a magnetic field to a superconductor or by placing a magnet above it, it creates surface current, and this surface current will produce a magnetic field to expel the magnetic applied field from inside the specimen. This is called as a Meissner effect, as we told. Let me show a small animation again downloaded from the internet, and it is a magnetic levitation experiment. And you see that there is a black superconductor, and in fact this is also a problem because it is a high temperature superconductor. It becomes superconducting at liquid nitrogen temperature. Nothing happens when it is just a metal, and this is a problem that is black, because if it is shiny, then probably the theory would have been better understood, and shiny means it is metallic, and because it is dull and black, it is probably not metallic, and that is where it creates a problem. We will just give a small illustration of that. Now, you see that there is an object which is put on the on this superconductor, and it is not collapsing down under gravity. It has been been pushed by the superconductor, and you see is further demonstration that there is nothing inside, and is nicely floated or floating there. And even if you give it a spin, nothing happens. If you try to put it close to that, it gets repelled, and that you can actually use it to sort of lift this superconductor, and that means that it is actually capable of doing some or lifting some weight. You see that weight is being lifted, and once the superconductivity is destroyed, then of course it collapses then onto the superconductor, which was earlier a superconductor at lower temperature. Now, you see that superconductivity is gone because you have the temperature is basically increasing. Okay, so let us see this levitation experiment we have shown, and if you want to know how much of weight it can actually lift, you see this thing that there is a sumo wrestler which is standing on top of these thing, and there is a superconductor below. Okay. So, it can actually lift very large weight, that is what it is saying. So, superconductors have electronic and magnetic properties, that is they have a negative susceptibility, which is what we have seen, acquire a polarization opposite to an applied magnetic field, and this is the reason that superconducting materials and magnets, they repel each other. when the temperature increases, the superconductivity is lost, and we have seen that these are different agencies that can kill superconductivity. Basically, these pairs that are formed are broken because of this additional energy coming from this, either the heat or from a current or from a magnetic field. How can you distinguish between perfect conductor, an ideal conductor, from a superconductor? So, on the left we see an experiment for a superconductor. So, this is called as the ZFC, which is a zero field cooled, and this is called as a field cooled. Okay, so, FC. So, if you take a superconductor and cool it, simply cool it, becomes a superconductor, then you put a magnetic field, it gets expelled. If you do it under the field cooled condition, that is, put in a field and then cool it, the result is the same. It gives you the same these superconductors at the end, which means that irrespective of whether you take a ZFC or a FC, you get this this picture, that is the magnetic field is pushed outside. This is called as the Meissner effect. So, what we are trying to come to is that the ideal conductors or good conductors do not show Meissner effect, whereas superconductors do. So, for an ideal conductor, if you do a ZFC, that is a zero field cooled, it becomes an ideal conductor. If you put a magnetic field, these flux lines are still expelled. If you put the magnetic field off, it just goes on to the conductor that we have started with. Now, if you do in a field cooled, so this in first you put it in a field and then you cool and you withdraw the field, you have these the flux lines are trapped inside, and this is the hallmark difference between a superconductor and a perfect conductor. So, if one actually has discovered a superconductor, one of the main experiments that establishes superconductivity being there is the Meissner effect. There are type 1 and type 2 superconductors and so on. So, this type 1 superconductors, these are the M versus or minus M versus H. So, you see that there is a superconducting state sharply sort of designating from a normal state at a given HC. These are called a type 1 superconductors, and their the magnetic field versus temperature dependence is pretty much what we have shown for the magnets, and outside it's normal metal, and inside the these region there is a superconducting state, and these are some of these things which are how magnetic field actually enters into the specimen, and magnetic field does not enter into the specimen. It just sort of falls within this lambda called as a penetration depth, and the wave function actually is it kind of builds up and becomes a coherent wave function inside a superconductor. Type 2 superconductors are more interesting and they are more common in nature. It has a sort of HC1, where the superconducting state actually sort of persists from between HC1 and HC2. If you see the triangular region there, so this dotted line is the basically the type 1 superconductor, whereas the type 2 superconductor, it bends down and continues to a different HC2, a larger HC2, and from there of course it is a metallic state, and one gets a vortex like state where the flux is actually trapped inside in the form of a vortex in this regime, where beyond the HC1. So, there is again minus M shown as a function of field, and again we show that how H actually varies inside a metal. Okay. It has slightly larger penetration depth, and the penetration depth by xi, that is xi is the coherence length, which is the size of the Cooper pair wave function, and lambda is the penetration depth, that is the how much of depth it can penetrate inside a sample. So, these k is equal, or this kappa, which is dimensionless quantity, ratio of the lambda by xi, and this lambda by xi is small or less than 1 by root 2 for type 1 superconductors, and for type 2 superconductors it is greater than 1 over root 2. Okay. And coming to the BCS theory, this is was proposed in 1957 by three people, John Burdeen, Leo Cooper and J.R. Schrieffer, and it explains superconductivity at low temperature and for conventional metals. And this Cooper realized that the atomic lattice vibrations, that is the phonons, actually are responsible for causing an attraction between the electrons, which allows them to pair up into pairs or teams that pass all obstacles and which cause these the resistance less, or I mean there is no resistance, basically that is a no resistance because of this pair. So, the picture becomes like something similar to this, that there were electrons earlier, and because of the lattice playing a role, somehow these electrons, individual electrons, they form bound pair. Once they form bound pair, they become non-interacting and one does not see another, and they, if you put on a small voltage or a bias, then the current will keep flowing, and this current will, there will be, it is going to be a persistent current with no decay of that current in a very long time. And Cooper really understood that there is some way this lattice vibrations play a role, and possibly the way he got this idea is from the isotope effect. And if there is an option or rather opportunity, I will explain what is isotope effect. So basically, these phonon frequencies that has this mass of the ions in the denominator as 1 by root over of m. Remember the lattice vibrations that we have done, and the Tc also has some behavior which is 1 by root over m, or inverse of this m to the power half. So, that way he might have inferred, and then of course, his intuition was correct. And it gave rise to this BCS theory, where there is a first microscopic theory, and it works very well for low temperature superconductors. It is a variational theory, it is not perturbative, there is no small expansion parameter. Superconducting gap is non-perturbative, which means that by doing any order of perturbation theory, you can't solve this superconductivity problem. Just like magnets, we have solved magnets, or at least the paramagnets and diamagnets using this perturbation theory. Here it is not possible. It predicts Tc, which are typically under 20 Kelvin or around 20 Kelvin at most. Phonons are important, as we have said. It explains London's electrodynamics, Meissner effect, etc. Everything is explained using this BCS theory. This is the paper of BCS. You see that it's 1957, and so it's here. Okay, so that's the date of this. It is published in Physical Review. So, Schrieffer, one of the recipients of the Nobel Prize for this discovery of BCS theory, he actually visualized this as a dancing room scenario. So, you see that the pairs are dancing. This has been taken from this internet. So, these pairs are dancing, and they are dancing in a manner that they are in sort of completely oblivious of each other. So, they keep dancing and not knowing the presence of another pair in the room. So, that is a dancing room scenario, and these pairs are like the Cooper pairs. So, the Cooper pairs, when they conduct supercurrent, they do not undergo any collision with other Cooper pairs, and that is why it is a dissipation-less current. Just a little bit of BCS theory. So, it is because of electron phonon interaction, and which Froelich and Pines and Burdeen, they have discussed in, or rather discovered it in 1950s. And if you take these electron-electron interaction via a bare Coulomb term, which is this is the Coulomb term in K space, that does not give rise to any attractive interaction. But if you add screening due to by electrons due to ions, we will show you a picture of that. You get some VQ, which becomes in the momentum space is like 4 pi e square by q square plus k square, where lambda is 1 over ks and q is the running sort of the total momentum of the two pairs. And so, this is kind of important in this discussion, in the initial discussion. We are still at the repulsive regime, there is no superconductivity, and if you consider an indirect process mediated by phonons, so that is between the electrons. I do not go into details. Once again, I refer to this course on superconductivity where I discuss this origin of this attractive interaction. So, what happens is that one electron, when it passes through the lattice, it sort of looks like these horses running in dusty fields. So, you do not see the horses, but you see some kind of ball of dust kind of moving ahead or moving farther. So, this electron, one electron going through the lattice picks up a lot of positive charge, just like this dust, and another electron seeing this a ball of positive charge gets attracted towards it, and that gives rise to a potential which gives rise this 1 plus omega q by omega square minus q omega q square. Well, omega is the the total energy of the two electrons, and omega q is the energy of the phonon, and there if you have omega square to be less than omega q square, this term can be negative, and it somehow, if it becomes greater than 1, there is a negative term in magnitude over sort of shoots these plus 1, then you will have a negative sign, effective negative sign arising in this equation, and that will give rise to superconductivity. A schematic picture is shown. You have in this kind of region, we have this superconductivity in the VQ versus omega region. So, if you really think about it, it is like a sort of a region formed where there is a small attractive region which is formed here, and this is V as a function of omega, and these attractive region will give rise to the superconductivity, and that will of course be possible as the temperature is low. So, this is a schematic representation of what I said, is that the first electron actually polarizes the lattice. So, the reddish region that you see is actually like a positive charge, another electron is attracted towards this concentration of the positive charge left behind by the first electron. You could ask this question, that why does not the first electron see the cloud due to the second electron? Now, this cloud is basically a quasi-particle, which is like a dressed particle, like that dusty horse, and that has much smaller velocity. So, if this positive charge has to see another positive charge, the time scale is much larger for that to happen, because these are slowly moving objects, because these are just polarization created by the electron. So, in real space, we have these two electrons forming a pair, which is analogous to this electron positron pair in nuclear physics or high energy physics. So, but in it is easier to visualize in real space, or rather reciprocal space, where there are these plus k and minus k mediated by phonons. They form a bound pair, and in the positron electron positron pair, that is by an electromagnetic radiation or a photon. So, the picture of course become very complicated, because you have several others, billion, 10 billion and so on, other pairs within a diameter which is xi, called as a coherence length. That is basically the extent of the wave function of this pair, of this Cooper pair. And all of these 10 to the power 7 pairs will contribute to the electron-electron interaction, and the value of xi, which we can estimate from this Fermi velocity etc., to be equal to some 1 micrometer. Because the positive ions, they take a long time to get going, because these are massive objects. By the time the electron has already sped away by distance which is beyond that coherence length. So, that is why there is hand waving, of course, a way of explaining how the pairs are formed, which finally gives rise to superconductivity. These are some of the facts there. So, these are momentum plus k and minus k of the 2 electrons, the total momentum is 0. They both are spin half. These one of them, the ms value is plus half and minus half, which means the electron of up electron and a down electron forming pair, and this by definition you know that is singlet pairing. So, the orbital momentum is angular momentum is 0, and of course, this vibrational frequency or this omega q is root over k by m. We have seen that how this k over m, where k is the force constant, which is a model for a solid, that these each atom or ion is connected to another atom or ion by a spring. So, that is the energy or the angular frequency associated with this. So, we have talked about this isotope effects, where these Tc is actually proportional to the Debye frequency, and the Debye frequency is a characteristic phonon frequency and so on. So, there is an involvement of phonons there, and we have also said that so this Tc actually goes as m to the power minus alpha, where m is the isotope mass. So, if you take two isotopes which differ by a small amount, the masses differ by a small amount. If you calculate the Tc, Tc goes as m to the power minus alpha, and for these superconductors alpha equal to half. Okay, so, alpha is half, means it is 1 by root over m, and this is also the dependence of the angular frequencies on the ionic masses, as you can see there, it is 1 by root over m. So, the phonons must be playing an important role, which is what Cooper had understood. To tell you a bit of discovery of superconductivity, it started in 1908 with about 4.2 Kelvin, then it about 1977 etc. it is about 23 Kelvin. 1986 there was a sudden surge and it went up to 164, even 170, close to 170 Kelvin under pressure. So, there the cuprates etc. they lie, and then of course, in the 2008 onwards there were some other superconductors that were discovered, which had of course lower Tc's, not so low, it is about 60 Kelvin most for these strontium, samarium, iron, arsenide superconductors, so to say. And this is how as time progresses, more and more superconductors were discovered, and these also got a Nobel Prize for this lanthanum barium copper oxide or lanthanum strontium copper oxide, that fetched another Nobel Prize to this for the discovery of the cuprate superconductors. And this is the picture of this Kamerlingh Owens, which we have said. So, these are some of the TCs recorded and some of the discoveries that you see there. These are Bednorz and Muller in 1986, which was one of the most studied material, and then there are many other discoveries. These are also of the same type, which are copper oxide is one of the main these things, and they went up to 134, 164 and all that. Some of these materials are also hazardous, that is why not very active research had taken place. So, just one or two slides on these high Tc superconductors, and these are there is still no theory, and because the normal state, the starting point is not known. Pairing is not phonon mediated, because phonon mediated would not have given rise to such large Tc. There are a lot of experimental data that contradict each other. Coherence length is too short. There presence of pseudo gap, I will tell you just in a while. There are no controlled expansion parameters, so perturbation theory is not allowed. Many other things. There is a very strange phase diagram where there is an insulator, antiferromagnetic insulator at low doping, this temperature versus doping. This doping is it's usually a strontium doping or barium doping, and there is a pseudo gap phase here, which means that there is a gap, a spectral gap in the metallic phase. This is a strange metal, which means that the Fermi liquid theory is not obeyed. In the over doping region, it is more clear that it behaves like more like BCS superconductors. So, all these put together have made these studies interesting for a very long time. However, there were no real consensus about these or microscopic theory about this superconductivity. Many things are known experimentally, but they could not reconcile all of them together, like the success that BCS enjoyed, BCS theory enjoyed, could not be possible for this. And there are these unconventionality, they lie in this, that superconductivity is by doping a Mott insulator. The superconducting dome and the Mott insulating phase, they are too close to each other. They are not L equal to 0 pairing. There are gapless regions from the angular resolved photoemission studies. There are gapless regions in the Fermi surface. There are pseudo gap in the normal phase. Copper oxide planes where the electron correlations are high. TC depends on doping concentration and also the number of copper oxide planes. It sort of has a violation or shows a violation with Landau's Fermi liquid theory. So, the developments for the last 2 decades are superconductivity in graphene at magic angles, ruthenets, iron based superconductors, topological superconductors, arsenides, nickelate superconductors. There are non-centrosymmetric superconductors such as BIPD, etc., granular superconductors, and so on. The infrared, the experiments that can detect superconductivity or the superconducting energy gap or the TC are the infrared emission, ultrasound attenuation, tunneling experiments, that is making a junction and put a bias and then makes the measure the current, and photoemission spectroscopy, NMR, nuclear magnetic resonance to probe short pairs, XRD to look at the crystal structures of this. So, just a summary of this. So, Kamerlingh Onnes in 1911 he discovered superconductivity at very low temperature. So, this is that plot that we had not shown earlier, but we are showing it now. So, there is a very sharp drop of TC at around 4 Kelvin. It is a 0 resistance state, that the resistance is less than 10 to the power minus 5 ohms. So, a superconductor and a good conductor will show a behavior like this as a function of temperature. So, the resistivity will or the resistance will sharply drop at some finite TC, whereas it will smoothly vary and go to a finite value at T equal to 0. So, sudden loss of electrical resistance below a certain critical temperature, sharp superconducting transition, expulsion of magnetic field, which are Meissner effect and perfect diamagnet, lossless energy conduction, and generation of very strong magnetic fields. Okay. These are some of the applications of superconductors. These are maglev trains, which were proposed to achieve it has achieved, a test vehicle has achieved a speed of 343 miles per hour, which is 552 kilometers per hour on April 14, 1999. And these rails that you see below are superconducting rails, and this whole thing actually floats. It does not have any wheels, and that is due to the Meissner effect. And then there are other applications in power cables, in this weight reduction of wind turbines and so on. And many of these are in the medical industry also. These are superconducting magnets giving rise to very large and uniform magnetic field to probe a non-healthy body. Okay. So, these are medical applications. And so, the superconductivity study of superconductivity does not end here, neither is complete in any form. But I propose that you have a look at various literature, and also if you feel the need, you can look at this course on brief theory of superconductivity. The course discusses at least the BCS theory in quite a bit of details, and it will benefit. We could only give a bird's eye view of magnetism and superconductivity. So, that finishes the module of solid state physics, where we have talked about phonons, the crystal lattice phonons, phonon specific heat, electrons, magnetism and superconductivity now. So, we will stop here. Thank you.